Hi everyone, thank you for checking out our presentation. I am Peter from the Flemish-speaking Free University of Brussels, and together with my colleagues we prepared a short presentation where you can see a novel FRF estimation method, especially developed for multiple input systems using short measurement, and we will present the results in a benchmark study style. So let's get started. We work in the field of system identification, which means that we have an unknown system represented by these black box, and we want to identify this system using input and output measurements. In this case, there will be a spatial drive wheel, what we will be identifying, and this we will do using the input and output measurement information to build frequency response function estimations. And this work and the presentation can be split into 4 parts. First, we will discuss the MIMO system identification problem. So MIMO stands for multiple input, multiple output. Then we will discuss the classical H1 estimation framework, the drawbacks of it, then our method, and the results will be shown by using the SEMI toolbox. I will shortly explain what this toolbox is. And of course, we will illustrate our results in an experiment. So, SEMI toolbox. SEMI stands for Simplified Analysis for Multiple Input System. You can grab your smartphone and scan these QR codes. Then you can read more about this toolbox and our work. So basically, it's a MATLAB-based toolbox where you can use the graphical user interface or command line as you wish. You can generate spatial signals which are very, very efficient for multiple input systems. You can analyze also measurements using arbitrary excitation. The toolbox itself is MATLAB and TestLab compatible, so you can import-export data. And the keyword is on semi-automated processing. So there are many types of estimators, parameters to be processed, and this is semi-automatically done in the toolbox. Here you can see an expanded view of the main GUI interface. So you can set yourself, for instance, these parameters, numbers of samples per period, period numbers, realization numbers, and so forth. In 99% of the cases, all these parameters, what you can see here, are automatically and correctly set up. And all research where this toolbox has been tested are in these fields. So the classical vibroacoustics, which is the main topic of this conference, but we also use for flow dynamics and thermodynamics. And the main advantage of this toolbox, if you use the proposed signals, then you can make next to a smooth and FRF estimation called best linear approximation, also additional information like nonlinear distortions and noise information. So this is something extra what you can use in your everyday practice. Okay, let's continue with the MIMO identification problem. For the sake of simplicity, here I consider 3 inputs and 2 outputs. In our example, in the paper, we have 5 inputs, so it's more complex. The baseline equation can be seen here. So it's the frequency domain connection between the frequency response matrix and the input matrix, which gives you the output. And I can split this term using these notions. So U1 stands for the first input, U3 stands for the third input. And what you can see here, we have a little bit of problem. We have 6 unknown parameters, so 6 blocks to be identified. But if you do only this, then we will have only 3 independent equations. So we have a rank issue. To solve this, what we can do, we can add additional experiments. So this was the first experiment, then we make another random experiment and another one, so that we have at least so many independent equations as blocks to be identified. I think it's fairly simple. This is the classical MIMO problem. Here the issue that this can be very time consuming, and in many cases, think of a shaker test can be technical failure. So we will have only short measurement available, and not always it's possible to repeat the experiments. So let's talk about this FRF estimation idea. If we take this idea situation, so we have here the idea baseline model, input, output, and the frequency response matrix. Then we can use the H1 estimator. It's very well known. Let's assume that we have also a steady state model, but now we have an observation noise on the input. This is more realistic. In this case, we can use the H1 estimator, let's say, with multiple periods, overlapping. Then we can have also this transient term. So here, noise transient term. In this case, we can use the H1 windowed version, for instance, Henning window, or the overlapped version with Henning window, for instance. And this, so the third case and the first case is considered in our paper. What we will do is a little bit different. So the proposed technique relies on this baseline model. So we have noise and we have transient. And this we consider as a line-by-line least squares problem. And that we know from system theory that the transfer function, so the frequency response matrix and the transient term are smooth. Smooth means that we can use, for instance, polynomial approximation. And let me illustrate this with a very, very simple simulation. So this is an FRF of a smooth system, the true FRF. Then I add some noise and transient, and these blue dots represent the output-input relationship. And what we do, we choose one point. Around this point, we select a narrow window, a processing window. I zoom in, and within this region, so in this rectangle, we do polynomials, let's say 0-order polynomial, first order, second order, third order polynomials. And we solved this polynomial problem within this interval. Okay? And if you do this continuously over the whole segment, data segment, what you can see on the screen, then you will have a very, very nice smoothened estimate. So we can estimate the frequency response matrix and the transient at the same time. The further advantage that this can be expanded to include multiple inputs. So using one block, one period, we will be able also to estimate an accurate frequency response matrix. Okay, let's demonstrate this with a real experiment. Here you can see a tire suspension system. We excite this tire suspension system at 5 points. And this measurement was used for component-based transfer path analysis methodology. And the keyword here that we need, accurate frequency response function estimates. We measure the input. These are the force signal and the output accelerations. The models what we use is the H1. This you can find back in the paper. Here in the presentation, we will use the best performing H1 windowed overlapped method and or local rational method, what you could see in the previous slides. And the error metrics, what you can see on the slides, are the so-called relative root mean square error. So we take the root mean square difference between the measured and simulated signal, and we normalize with the root mean square of the measured signal. Here you can see the experiment. We used so-called pseudo-random noises in our toolbox called multisigns. These are here the basic information. So 1600 Hz sampling frequency with 2048 samples in one period, which results in a frequency resolution of 1.28 Hz. Here you can see the 5 excitation points in frequency domain. So these are the signals and these are the noise estimate. So we have a good signal to noise ratio around 40 decibel, as we would expect. In total, we have 11 independent random realizations. And per realization, we have 22 repeated blocks, so 22 periods. We can do a quick transient analysis just to have an idea. On the left here, you can see one of the output channels, the first 3 periods. So this is the time waveform. And here in the second figure, you can see the differences between the last block minus the first, second, and third block. Here the assumption that the last block is already in steady state, and the differences are shown in decibel scale. It's important because we know that the transient decays exponentially. So when you illustrate this in decibel scale, you expect to see a line, and indeed you can see that here we have a transient. So the first block is disturbed by transient. Okay, let's start with the most challenging case. This is the worst case scenario. This means that we have 0 delay block, 1 realization, and 1 period. In other words, this is the very, very first block. To make things simple, I selected only one, the most problematic output channel. And in orange, you can see the frequency response function estimates of the H1 windowed overlapped estimate with approximately 90% root mean square error. And in blue, you can see the local rational methods or all proposed method with a root mean square error of 4.5%. What does this mean? How we get these numbers? So the trick here that we build a model and we cross-validate this model on an entirely independent data set. So we take out the last random realization and we test how accurately we can predict the last remaining blocks using our model. Okay, so let's see an ideal scenario. This means that we have 5 independent realizations and 1 period. So officially, we have as many random realizations as many inputs, so we can solve this problem easily. And still, I do not skip any blocks at the beginning. So this means that we have also transient in this data. Again, orange shows you the frequency response function estimates for the H1 windowed case with approximately 11% error, and the blue shows the proposed method with approximately 3.5% error. And check the very best scenario. This means, sorry, it's the good scenario. The very best is to come. So we have 0 delay block. This means that we use the transient disturb blocks. We have 10 realizations, so double as many as officially needed to solve the classical MIMO problem, and 1 periods. And as you can see that the local rational methods is steady around 3.1% error, and the H1 window estimate got 6.6% error. It's better, but still not perfect. And now comes the best case scenario. So here I skip 1 delay block, so we have only transient free data. The results are better. So the LRM is now less than 1% in terms of error, and the H1 is 1.8%. But I'd like to draw your attention to the last FRM block. As you can see, the classical method has really problem processing this channel. As you can see, it looks very, very noisy, whereas our proposed estimate looks much, much reliable. To sum up, the results are very good. This means that you can estimate multiple input data using only 1 block. Given some assumptions fulfilled, this you can read in the paper. You don't need to be a scientist, you don't have to really do quantum physics. It's quite a simple, straightforward method. There is no tuning method needed. You can solve everything as a least squares problem. The price, what we have to pay, that it's a little bit slower, but not as much as you would expect. Let's say in this configuration, the processing time took 3-4 times more than the H1 processing time. And if you want to read more about this technique or about or related projects, I invite you to scan this QR code. Thank you very much for your attention.